Okay, so this is homework 5.2.1, which is over limits. And the front side of the homework gives you graphs. I'm going to run through number 1 and number 2, at least partially. Make sure you guys understand what the limits are actually asking you to do, and the things that limits actually care about. So for example, number 1, I've given you the graph right here. The very first thing that it asks you on part A is what is the limit as x approaches 2 of your function f of x. And so all you have to figure out is, here's where x is 2, right here, okay, right along this line right there. And so what you have to figure out is, what is your graph doing as it approaches 2? So as I come in from the right and I approach 2, I'm approaching this hole. And as I approach from the left, I'm also approaching this hole. And the limits don't care if the hole is there, because that's not what it's asking me. It's saying as x approaches 2, y simply approaches what number? Okay, and the number that the y value is approaching is just 1. Okay, but then they ask you what actually is f of 2. And they're trying to drive home the point that the limit didn't care that the hole was there. When x actually is 2, the place where there actually is a y-coordinate, a solid dot, is also with a y-coordinate of 2. It's this point right here. And so f of 2 is actually 2. Okay? But what limits do care about is when there's breaks in the graph. So then they ask you, what is the limit as x approaches 3 from the positive side of f of x? So we're going to go to where x is 3. Okay, that's along this line right here. Doesn't show up super well with my stylus here. And this is saying go to the right of 3, turn around and head back towards 3. Okay, so I go to the right of 3. That puts me on this section of the graph right there. And I turn around and I head back towards 3. As I do that, I am getting close to this y value right there, which is 2. Okay, this is what we call a right-hand limit. Then the next thing that they ask you is, what is the limit as x approaches 3, but from the negative side or from the left? And so the superscript, it's not an exponent, the superscript is telling you whether you're above 3 or below 3 when you are approaching 3. That's what it's telling you. And so this, of course, is what we call a left-hand limit. So we're going to go to the left of 3. That puts us on this section of the graph. And as we head towards 3 from the left, we are now approaching this y value, which is down at -1. And then the final thing that they ask us regarding this part of the process, the limit part of this particular problem, is they actually ask you what is the limit as x approaches 3, and they don't specify a direction. And so they're asking you, what y value are you approaching as x approaches 3? And your answer literally is, well, it depends on what direction you come from. And since these two answers don't agree, and you approach a different y value depending on which direction you are coming from, the limit does not exist. Okay? And it doesn't matter that on both sections of this graph, you were approaching a hole. That doesn't matter. So the next thing they ask you is, what actually is f of 3? Because that doesn't actually matter when it comes to evaluating the limits. And the point that actually has an x-coordinate of 3 has a y-coordinate of 1. Okay? And then the final thing that this problem asks you is, what is the limit as x approaches 4 of your function? And there's no jumps or breaks. When you're approaching 4, when you come in from the right, you're approaching the same y value as if you come in from the left, and that y value is 1. And so that's the limit as x approaches 4. So that's question 1 on the homework. Question 2 is very similar. It just gives you a new graph to start over with. So the first thing that it asks you is, what is the limit as x approaches 1? of your function, f of x. And so when x is approaching 1, that puts you firmly in the middle of this interval of your graph. And as you approach 1 from the left or from the right, you are approaching this hole, and it has the same y-coordinate from both directions, and so the limit is just 1. Then the next thing that it asks you is, what is the limit as x approaches 2 from the negative side, or from the left side of 2? So, I clear up my picture a little bit. Okay, the 2 is where the graph has a break in it, right there. So if I'm going to start out on the left of 2, that once again puts me on this interval of my graph. And so as I approach an x value of 2 from the left, I'm approaching this y value, which is 1. But then they ask me, what is the limit as x approaches 2 from the positive side, or from the right of 2, or from above 2, which now puts me on this section of the graph. And so as I approach 2 from the right side, I'm now approaching this point, which has a y-coordinate of 2. And once again, because these two are not approaching the same y value from both directions, when they then ask you, what is the limit as x approaches 2 of the function in general, as a whole, your answer would be does not exist. Okay? And they do ask you for the solid dot again. This one, I think, did have people confused because they thought, oh, well, this time the solid dot actually was on one of the two branches. The whole point of doing number 1 and number 2 is to illustrate that it doesn't matter where the solid point is, because limits don't care where the solid point is. But f of 2 actually is 2 in this case. And then the limit as x approaches 3 of your function, as you approach from the right and from the left, you are approaching this hole right there at a y value of 2. And it doesn't matter that the actual function value at 3 is 1, because the solid dot is actually below it, because the limit didn't care about what point do you actually hit when x actually is 3. Okay? Now, most functions can be easily calculated, their limits, just by plugging the number in. And so the problem with the back is that we really should have made you guys do more problems than just these, because they really didn't give you a ton of practice with each situation. But what problem 5 has you run through is, this is a rational function, but this rational function has a denominator of x minus 5, and the numerator factors as x plus 2, x plus 1. Not that you have to have it factored, I'm just trying to remind you that there is no whole. So there's no simplifying step in this equation. Okay, so you wouldn't have to worry about that. The other thing is that since there's no whole, there's no simplifying to do, we know that the only place that this graph is going to have a discontinuity is at its vertical asymptote. And that vertical asymptote would be at x equals 5. So what we notice is that here, they're not asking us to evaluate the limit as x approaches 5. They want to know what the limit is as x approaches 1. And so, not that I would say we need to graph this, I just want to refresh your memory what this graph would look like. It's top heavy. It's going to have an oblique asymptote, and I don't really know where the oblique asymptote is. I'm not actually going to do the division, but what it would look like is something basically like this. Okay, and so when they ask you for the limit as x approaches 1, you are going to be firmly on one of the branches of the graph. You're not going to be anywhere near a jump or vertical asymptote. And you can see that because what's going to happen is if you actually just took that 1 and you plugged it into the equation, 1 squared is 1, plus 3 times 1, which is 3, plus 2, and then 1 minus 5 in the denominator. You would get a 6 on top and a negative 4 on bottom, and so you would get negative 3/2. You actually just get a nice, neat answer. And so that tells you what your limit actually is. So number 7 is the first time you're going to run into a problem. Okay? On number 7, initially you have a similar looking situation. You have a rational function. Okay? This particular rational function would factor on top as x minus 2, x plus 1. The denominator is x minus 1. So once again, no simplifying, no holes, nothing to worry about. But this time around, we would have a vertical asymptote at x equals 1. And this time we're actually being asked to calculate the limit as we approach that vertical asymptote. And if you watched the video that I did on limits, hopefully what you understand now is that it really doesn't matter what our graph does at that vertical asymptote. The answer is going to be does not exist. If it's a vertical asymptote, it's one of those two situations that I discussed in that video. In this first situation, so if I have a vertical asymptote at 1, the first situation is that the two branches might diverge at the vertical asymptote. And in that regard, it does not exist because you're not headed to the same y value. As x approaches 1, one side is approaching one direction, one side is approaching another direction. The second scenario, if you have a vertical asymptote and your graph behaves like this, what we could say is, oh, well, as x approaches 1, my y values are headed up to positive infinity, but infinity is a number that you can't ever get to. You don't actually know what number it is. How big is it? Can you ever reach it? And so since you can't tell me what y value are you actually headed towards, because infinity is not actually a real number that you can head towards, you're just headed in the general direction. And so you still say does not exist. And infinity is one of those difficult math concepts. I mean, infinity plus infinity is still infinity. Infinity times 2 is still infinity. Infinity to the power of infinity is still infinity. So that's why you can't ever definitively say, oh, I'm headed towards this one y value. Okay? And so that's why it does not exist automatically as soon as you've determined it's a vertical asymptote. But then the remaining problems run you through completely different scenarios. So what number 9 runs you through is actually a scenario that I've addressed in an earlier video tonight. This one's going to have a hole. Okay? And so this is not the easiest equation to notice it right away in. And so what a lot of people might do is they might go ahead and they might try plugging negative 9 into the equation thinking, oh, I'm just going to get my answer. So what would happen is this. You plug negative 9 in. Okay, negative 9 squared is 81. Negative 9 times 11 is minus 99. And so you end up with 0 over 0. It's like a blaring sign that says, hey, there's a hole in the graph. And remember, the limit doesn't care that there's going to be a hole there. You can still calculate the limit if there's a hole in a graph. But you can't actually calculate the y-coordinate for that hole if you don't simplify the equation first. And so what that 0 over 0 is telling us to do is it's telling us to factor and simplify that equation. So we would take our denominator and factor it, and it factors nice and easy as x plus 9 and x plus 2. And the x plus 9's cancel. And so we are simply left to evaluate the limit as x approaches negative 9 of this now simplified equation with a 1 in the numerator and an x plus 2 in the denominator. And so now we can plug negative 9 in successfully. So now when we plug negative 9 in, we get negative 1/7 as our limit. And that would be the y-coordinate for the hole on that graph. Okay? And then 11 and 13 give you two even funkier situations. Okay? So, on 11, you start out, just like actually you did on number 9, you start out thinking, okay, I'm going to plug 0 into this equation. I'm going to see what I get. Okay? When you plug 0 into this equation, what you get is 1 over, plug 0 in right there, and you get a 1 in the denominator of that embedded fraction. And so you get 1 minus 1 over 0, and so you get 0 over 0 again. The problem is that up until limits, up until 5-2, the only 0 over 0 you had seen were rational functions that could be factored and reduced. This equation is going to require a different method, and it's one that we looked at quite a while ago, much earlier in the year. So I'm going to refresh your memory on it. Whenever you have embedded fractions inside of a larger fraction, what you do to simplify your equation, because remember that's what 0 over 0 is telling you, is it's saying simplify, right? Is you multiply by the denominator, or in some cases the common denominator, of your little embedded fractions. So the denominator for my only little embedded fraction is x plus 1. So that's what I'm going to multiply my whole equation through by. So I take x plus 1, I distribute it to the first part of the numerator, and it's going to cancel out the x plus 1 in this denominator with that, and it's going to leave just this 1 right there. So limit x approaches 0, that just leaves a 1. But then I also have to remember to distribute this x plus 1 right there to that minus 1. And I'm going to show it as two separate steps. Some of you are confident enough to remember to distribute without showing the step. I'm actually going to write it out. That negative 1 right there needs to multiply to the x plus 1. And then I also need to take this x plus 1 and multiply it to the denominator. And I'm going to leave this one in factored form. Okay, so I'm going to be evaluating the limit as x approaches 0. I distribute the negative 1 through the parentheses right there, and my numerator becomes 1 minus x minus 1. And so that means that the 1's will now cancel. So I'm going to evaluate the limit as x approaches 0 of negative x over x times x plus 1. And now the x's will cancel. And so ultimately I'm able to simplify my equation into this final form. The limit as x approaches 0 of, I was able to reduce everything out of the numerator down to a negative 1. And I'm left with just an x plus 1 in the denominator. And now I can plug 0 in safely. When I plug 0 in, I end up with negative 1 as my answer. Okay. And so technically 13 is the same exact type of problem. Okay, but let me go to the next screen. There we go. Okay. Because I've got a big fraction with little fraction or 2 embedded in it. But this time, we're not going to end up with 0 over 0. Okay, so this is the final situation that the homework tries to run you through, and they just didn't give you a ton of each type of practice. Okay, so once again, you start out and you think, okay, I'm just going to plug negative 4 in. I'm going to see what I get. So I get negative 4 on top. Can already tell I'm not going to get 0 over 0. But when I plug negative 4 into this fraction right here, this is what I get. Okay, I now have a problem. Most of this fraction looks okay, but this embedded fraction is undefined. And so that means that in the midst of trying to simplify this, my very first thing that I would need to try to do would be to combine these two fractions down here, and I can't do that. because one of them doesn't exist. And so this is a different form, a different indeterminate form than we've ever seen before. But the method for simplifying this equation is actually the same as number 11. We're going to multiply our entire equation by the common denominator. Now this time, however, we have two embedded fractions in our equation. And so we have to come up with the common denominator for both fractions. And that common denominator is going to have the 4 and the 4 plus x. So there's our least common denominator for our embedded fractions. And so I take this, multiply to the numerator, and I'm going to leave it in its factored form. I'm going to have my 4 and my x and my 4 plus x. When I distribute, I don't have any idea how I just did that. I don't know why it just moved. Okay, well, let's try not to move it anymore. When I take this denominator and I distribute it to the first fraction, right there, it's going to, this 4 plus x is going to cancel out with this 4 plus x, right there. And so I will have this 1 times this 4, which is just 4. And when I take this and I distribute to the second part of the denominator right there, the 1/4 and the 4 would cancel instead. I'm still going to have that minus sign that I need to make sure that I remember, and I will still have the 4 plus x. And then what I would need to do is I'm going to leave the numerator in factored form, but I'm going to distribute the minus through here. So 4 minus x, and the 4's will cancel. So I'm going to be doing the limit as x approaches -4 of 4 times x times 4 plus x all over -x. And so the x's will now cancel, and this just becomes a -1. And so I will now, my simplified equation that will actually allow me to evaluate the limit is going to be the limit as x approaches -4 of -4 times 4 plus x. Now this one does, just coincidentally, this obviously does not always work out this way, but when we plug -4 into this equation, we end up getting 0 as the answer. But at least we actually got an answer this time. Okay, and we did not get an answer the first time. So I hope that helps. Hope you guys feel ready for your quiz on Sunday or Monday. Just message me or something if you need anything else.